Here we're going to talk about the Fibonacci sequence. Now, Fibonacci is not the name of an actual mathematician. The mathematician who this is named for is Leonardo Bonacci, and he became known as Fibonacci through the last, say, 800 years. He was from, I believe, the 1100s or 1200s, sometime back then. Now, to define this sequence, it's a very famous sequence of numbers. Now, it's defined recursively. And F1, we're going to label the numbers in the sequence capital F with a subscript. The first number is 1. The second number is also 1. But then, after this, the next number is the sum of the previous two numbers. So Fn plus 1 equals Fn plus Fn minus 1, and this is for what? For n greater than or equal to 2. Because we already defined it for 2, so we want it to start being defined for n equals, for subscript 3, I should say. So now, let's find a bunch of numbers in the Fibonacci sequence, and I'm going to write them just as a string of numbers. So I'll say the numbers in the Fibonacci sequence are, and that says the numbers in the Fibonacci sequence, SEQ, abbreviated, are, well, we're given 1 are the first two. So what's F3? Well, F3 equals F2 plus F1. Let n equal 2 down here. F2 is 1, F1 is 1, so that's 1 plus 1, which is 2. Now, I find this a lot more confusing than just looking at the string of numbers and adding the previous two numbers. You can even see, when I was explaining it, I hesitated because of all the letters and numbers all over the place. With this sequence, it's much easier to just look at the string of numbers and add the previous two. So 1, 1. The next one is 2 because 1 plus 1 is 2. The next one is the sum of the previous two numbers. 1 plus 2 is 3. The next number, the sum of the previous two numbers. 2 plus 3 is 5. The next one, the sum of the previous two, 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13, 21. 21 plus 13, 34. And I'll keep going down here. I don't want to write on the wall. 21 plus 34 is 55. 55 plus 34 is 80 plus 9, also known as 89. 89 plus 55, 144. Yeah, 130 plus 14, 144. And so let's do the next one. 233. 89 plus 144, 244 minus 11, 233. The next one, let's do one more. 377, because those added nicely. Now let's do one more because they add nicely. 610. And so on. So if we wrote as an example to find a few of these, well, you would look in that sequence and find them. If you weren't given the sequence, you'd have to come up with it. Just as an example, find F3, F9, F12. Do we have enough numbers for 12? Yeah, I think we do. F3, well, the third digit in this sequence is 2. F9, what's the ninth digit in this sequence? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 34. I guess I could have gone larger than 12. Well, whatever. That's 9. F12, 10, 11, 12 is 144. Now, these numbers show up amazingly frequently in nature. And I have a list of a few examples. Petals on flowers. These numbers show up a lot. Examples. A flower with one petal exists, the white calla lily. I never heard of it, but it has one petal. Flowers with 3 petals. Lilies and irises have 3 petals. 5 petals. A buttercup and a wild rose have 5 petals. 8 petals, many delphiniums. Never heard of them, but they have 8 petals. And there are flowers with 13 petals, ragwort, corn marigolds. Never heard of them. But they have 13 petals. Flowers with 21 petals. Asters and black-eyed Susans. And there are daisies with each of 34, 55, and 89 petals. Those are daisies. So these numbers show up a lot in flowers. Where else do they show up? They show up in leaf arrangements, meaning if you have a branch and on it leaves are forming, they will, in a way, show the Fibonacci sequence, or show some of these Fibonacci numbers in their leaf formation. So if you have a leaf pointing in this direction and you go up the branch, the next leaf will be pointing, say, in that direction. You keep going up in that direction. But eventually you're going to get one that's also pointing in the same direction as the first one. And between them will be the space between them can be, or is given by a Fibonacci number in many branches. Pine cones. I have an example on my phone showing the pine cones, but a pine cone, I'll show the example on my phone when I get there. Snails show the Fibonacci sequence in their shells. Other seashells, peacocks, show it. When Stradivarius was making his violins, he used some consequences of the Fibonacci sequence. Either, I'm actually not sure if he intentionally did. The source I was reading said he intentionally used the Fibonacci sequence in his constructions. I'm not sure if he used these numbers or if he used something we're going to talk about at the end of this video called the golden ratio. But he used one of those two in his constructions. The golden ratio, a consequence. The golden ratio is something that can be seen using the Fibonacci sequence. And we'll see that in a moment. Debussy, a composer, a French composer from the early 1900s, late 1800s, used the Fibonacci sequence in his music somehow. I am not a Debussy fan, so I wouldn't know any of the music, but the internet told me that's one of the places where it was seen. It also said Mozart used it in some of his sonatas, but then it didn't say which ones, so I don't know about that. But next time I listen to the Mozart sonatas, I will see if 89 shows up or something. Now, they also show up in bananas. You take a banana, I'm sure everybody has noticed that if you take a banana and try to split it in the long way, it splits almost always into 3 pieces. Every banana I've seen is split into 3 pieces. The textbook and the internet said there are bananas that also split into 5 pieces. Go figure. If you've seen a banana that splits into 5 pieces, or a brand of banana, let me know. I've never seen one. Cauliflower shows Fibonacci numbers. Broccoli shows Fibonacci numbers. Lettuce shows Fibonacci numbers. And pineapple show. Pineapple's the actual big pineapple with the outside and the leaves on top shows. They show the Fibonacci numbers. In particular, they show Fibonacci, what are known as Fibonacci spirals, in sets of 8, 13, and 21. So I'm going to show you a couple examples on my phone. I'm going to try to show it at the camera. It's also, Fibonacci numbers are also present in the distance in DNA molecules, or DNA. I don't know if molecules is the right word. Now, what do I mean by these spirals? Well, if we look at this right here, let's see. I hope that shows up clearly in the video. This right here is a picture I found online of a pine cone. And you'll notice, it's the same pine cone, and it has these lines. I think they're yellow or green or something. I'm colorblind, so I'm going to call them yellow. Notice in the pine cone on the left, maybe I should hold this in the actual camera, the reflection of, okay. In this one on the left, you follow these, my pen tip is metal, so it noticed that. In this, if you follow this the leaves on a pine cone, they actually form spiral type things from the bottom of the pine cone. And they're in a pattern, and you can go in this direction. You go all the way around this pine cone. It has 13 of those arcs of pine cone leaves. They're called whorls, W-H-O-R-L-S. 13 whorls on this pine cone going in that direction. Now if you go in the other direction, it forms whorls as well, different whorls. In this case, if you follow them on this pine cone, there are 8 such whorls. So when I said a pineapple has Fibonacci numbers showing up in spirals in 8, 13, and 21, this is what I meant. If you look at the bottom of a pineapple, let's see, all of my pictures are showing. Let's see, are there any pictures I shouldn't be showing? You never know. No, okay, that looks good. In a pineapple, if you look at the bottom of a pineapple, it'll look kind of like this pine cone, and you can count the whorls going in the 2 directions, and they will be Fibonacci numbers. Now, I have another picture of a peacock. So here, this is another picture I found online. This is not a picture I took of a peacock. On this peacock, on its feathers, it has like circle type things that look kind of like eyes. And the person who made this picture took the feathers and just drew them as lines so that the intersections of the lines were where those dots were. And then this bottom picture shows that a little more clearly without the peacock. Now, again here, those whorls on the peacock where you follow those eyes are Fibonacci numbers. In this case, they're both 13. In this direction, they're 13. In the other direction, they're 13. And that's just a sampling of the types of things, the types of places that this sequence of numbers shows up in. Now, that's not to say it always shows up. It's just surprisingly frequently how much it shows up. Like, for example, there are flowers with 4 petals. The textbook, or maybe it was the internet, I forget, one of them said that the fuchsia is a flower with 4 petals. So not all of them have this, but many of them do. And in nature, well, like when leaves are forming, they will form best when they get the most sunlight and so on. They get the most sunlight, they have the most area where they can collect rain so that the water can travel down to the roots or something like that. And when they form, for example, these petals or these leaves, they go out in certain directions, and as a result of that, these numbers show up. I'll mention a little more about that later when we talk about the golden ratio, and we'll get there in a moment. Now, we talked about the Fibonacci spiral that shows up on pine cones, shows up, we talked about on pineapple. Now, there is another type of Fibonacci spiral that shows up, and it's something I would guess several of you have seen before. So let's draw that. This is not erasing now. Why is that erasing so poorly? Okay. So let's, I need my marker. That's a pen, not a marker. So let's draw another Fibonacci spiral. So there are 2 different things I could mean by Fibonacci spiral. The whorls on a pineapple. I mean, I first didn't call them whorls because if I said whorls, people wouldn't know what I was talking about. Spirals, whorl. So let's another Fibonacci spiral. And we're going to form this geometrically. And how are we going to form it? Where do I want to draw the first squares? Let's draw the first squares here. We're going to start with 2 squares which are 1 by 1. Let's make them look kind of similar. So we're going to form squares with side lengths of those numbers. We're going to start with 2 1 by 1 squares drawn next to each other. Well, next we need a 2 by 2 square. And we're going to draw that up here, because right here, those two ones combine to make a 2. So we're going to throw a square on top of that. And now we're just going to keep going around forming squares, 3 by 3, 5 by 5, 8 by 8, and so on. So here I'm going to go clockwise. We have a 2, and we have 2 ones. So over here, we're going to get a 3 by 3 square. And I'm not going to actually draw those numbers in there. But that 2 and that 1 will give us a side of length 3. So now we have a 3 by 3 square. Next, 5. Well, 3 plus 1 makes a 5, and then we can make a 5 by 5 square. Well, then we're going to go on this side and make an 8 by 8, because we have a 5, a 2, and a 1, or 5, a 1, and a 2. That makes an 8. So here's an 8 by 8 square. And then I'm going to put another on top. The top has length 13, because it's 8 plus 2 plus 3, so that's 13. So that'll give us a 13 by 13 square. And I'll draw one more square. The next number is 21, and we'll draw it on this side. Notice we started 1, 1, 2, 3, 5, 8, 13. So we started here, and then we went around this figure in a counterclockwise way. So here, that's more of a rectangle, but that's okay. That'll be our last one that we draw here. You could keep drawing that, and that'll be, what, 21, I think was the last number I said? 1, 2, 3, 5, 8, 13, 21. Yeah, okay. So right here we have this arrangement, and I'm going to draw something using arcs of a circle, starting down here and working our way to the middle by going diagonally in each diagonally in each square. Sorry, I just got something in my throat and made me cough and unable to talk. So here I'm going to use arcs of circles to make a spiral by going diagonally in each square. What do I mean by that? Well, pretend that's consistent there. Then we're going to do that with the next square by going diagonally. Then we're going to keep going around diagonally in each square until we make our way to the middle. And right here, this forms a kind of spiral that looks, I guess my hand drawing doesn't look as spirally as it could. But this spiral shows up frequently in nature. The spiral kind of looks like that. That's known as the Fibonacci Spike. I guess it went around a little more. Fibonacci Spiral. Now, where does that show up? That shows up on what? On a nautilus shell. The nautilus shell looks like that spiral. Many of you might have seen a picture of a woman with long hair flicking her hair back, or maybe I should say long hair, with water, flicking her hair back in water, and then the water forming a kind of spiral. That is this spiral as well. Another place it shows up is on the ear. The ear, if you take this right ear and look down like this, I guess this is the lobe. The upper portions of the ear, I don't know what these wrinkles on the ear are called, but this spiral shows up there as well. It shows up, I mean, not all pieces of it, but it shows up a little in some of those pieces in the upper portion of the outside of the ear. Oh, one other thing that I wrote down here. If you've ever watched a hurricane on a radar, the hurricane, maybe not even radar, on the maybe if you've seen a hurricane picture from the space station and you've seen it move, it takes this spiral shape as well. And this we formed just using areas of, or not areas, we're using side lengths of squares following the Fibonacci sequence. Here we're going to talk about the golden ratio. And we're going to actually derive the golden ratio using a little bit of algebra. Behind the algebra, there is actually some calculus knowledge, but I don't think we'll actually need to worry about that too much. Now, the golden ratio, what we're going to do is find ratios of consecutive Fibonacci numbers. And we're going to look at these ratios. So ratios of consecutive, we're going to take the second and put it over the first. So here we have 1 over 1, and that equals 1. We're going to write this as the decimal. Then the next ratio, we have 2 over 1. So 2 over 1, that's a comma. Reduces to 2. The next one, 3 over 2. That's what, 1 and a half. And I'm going to write the decimal. I don't like decimals, but they're good for this. Next, we have 5 over 3. That's about, these will be approximations, about 1.66, unless they're exact. Next, we have 8 over 5, which is what, 1.6. Next, we have 13 over 8, which is 1.625. Next, we have 21 over 13, which is about 1.615, and so on. Now, you can keep going because this sequence keeps going. You can keep going 34 over 21, 55 over 34, 89 over 55, and so on. Now, these numbers look like they're all approaching a certain number. And they actually do approach a certain number. 1, 2, 1.5, 1.66. Notice these are all 1.6 something. So you might suspect, what do these approach? You might suspect they approach an actual number as you keep going. And they do approach a certain number. They approach what is known as the golden ratio. 1 plus root 5 over 2. Now, why is it a golden ratio? We're going to derive that number in a moment. Why is that called the golden ratio? Well, one reason it's called the golden ratio is because if you take, this is not drawn to scale, it is believed that a rectangle with sides in the ratio 1 to 1 plus root 5 over 2 is the most aesthetically pleasing rectangle there is. So this might not be drawn to scale. I don't know if that's the most attractive rectangle in the world. I don't like it all that much. So I'm guessing it's not drawn to scale. Now, why do these numbers approach that? This number maybe has a decimal, I should say. And that's just a number. This is about 1.618033. So 1 to about 1.6 is a very attractive rectangle, supposedly. Now, why do these ratios approach that number? Well, let's set it up algebraically. So remember, what we're looking at here is the ratio of consecutive Fibonacci numbers. So Fn divided by Fn minus 1, a number divided by the one before, a Fibonacci number divided by the number before. Well, what is Fn? Fn is just Fn minus 1 plus Fn minus 2, because Fn is the sum of the two numbers before. So Fn minus 1 plus Fn minus 2. Now this fraction reduces. We can reduce this fraction by, splitting it through that addition sign on top. We can get Fn minus 1 over Fn minus 1 plus Fn minus 2 over Fn minus 1. And of course, this first thing is something divided by itself, so that's just 1. So that's just 1. Well, that's great. We have this relatively complicated looking equation. But remember what we're looking at. This we're looking at what happens as we let this ratio go on toward larger and larger numbers. So let's say that as n goes to infinity, this ratio goes to x. So let's say that that ratio, as that sequence goes on, let's say that that approaches a number x. We know what it is. We know it's 1 plus root 5 over 2, but we're going to derive that. So we don't, right here, we don't know what it is. We're just saying it exists. And let's call it x. And what does that equal? Well, using this equation over here, equals 1 plus something. What's that thing? Well, this is fn minus 2 over fn minus 1. So this first ratio is things like 2 over 1, 3 over 2, 5 over 3, 8 over 5, and so on. That last thing over there is things like 2 over 3, 3 over 5, 5 over 8, 8 over 13. In other words, it's this thing flipped around. It's moved back a position because it's, what, n minus 2 and n minus 1. But it's really, as this ratio goes off toward the end of the sequence, it's really this thing flipped around. This ratio flipped around. It's really x flipped around. Flip around x, you get 1 over x. And now we want to solve this equation for x. Because if we solve it for x, we will get what happens as this ratio goes toward the end of its sequence. Now, how are we going to solve this for x? Well, I don't like that fraction. So let's multiply everything by x. Let's multiply everything by x. Let's multiply the first thing by x, you get x squared. Multiply that by x, you get x, not 1. Multiply this by x, you get 1. So now we want to solve this for x. This is a degree 2. So let's put everything on one side. X squared minus x minus 1 equals 0. I'm going to solve that over here. So x equals, you could try factoring. It won't factor conveniently. We will use the quadratic formula. Negative middle term, so negative negative 1 is positive 1, plus or minus square root of middle number squared, 1. Negative 1 squared is 1. Minus 4 times 1 times negative 1. So minus 4 times 1 times negative 1 is plus 4, all over 2. And this equals 1 plus or minus root 5 over 2. And these numbers are all positive. Their ratio is going to go to something positive. So in this case, since we want, so I'll just say only x equals 1 plus root 5 over 2. Because we're looking at the ratio, so this ratio is the ratio of positive numbers, so we're not going to have 1 minus root 5 over 2, we'll just have a positive. So right there, we used algebra and the definition of the Fibonacci sequence to derive the golden ratio. Now, before we did this, I said there would be some calculus in here. The calculus is this arrow. One thing you do at the beginning of a Calculus 1 class is talk about limits, meaning what happens as something goes to infinity. So here, we're actually looking at a limit. So if going from here down here was confusing, that could be because you've not seen calculus in all likelihood. But remember, this x is just saying what happens as this ratio goes toward the end of its sequence. Now, I'm not going to ask you to derive the golden ratio using this. This was just so you could see how we can use algebra to do this. So I will not ask on any test or any homework to derive that formula. But it is nice to know. I actually never saw it until I'm teaching it right now. I never saw this derivation of it. So I think it's good to know that we can use algebra to help us solve what looked like a geometry problem, or what looked like perhaps a sequence problem.